Right, so here we have my setup for the Cavendish experiment, which is an experiment which I will find the date of when it was originally done, but it was not too long after Newton's theory of universal gravitation predicted the existence of a gravitational constant and declared that all masses attract, that someone Cavendish, whose name I will find, used this experiment to measure the gravitational constant. He used 4 known masses, and in his case he used a torque meter, but I will be using the acceleration, which isn't quite as accurate, but still should get in the right ballpark. Used this system to measure the universal gravitational constant. It has the 2 light masses. They go on the rod, balancing it and allowing it to rotate freely. You then also have the 2 heavy masses, which are there to attract the 2 light masses and cause the entire spring system to rotate about its centre. They will apply a constant force, near enough because the range is so small, that will cause the system to accelerate in a circular motion very, very slowly. But through time-lapsing I hope to be able to capture that and show the acceleration of the rod, and thus to get an approximation of the gravitational constant, which I will be comparing to the one in common use. The first step is to measure the masses involved. Then I will go through discrediting variables, which you can see several methods here, and proving that I did not fake it. I know there will be people out there who still think I fake it, but I will make it the job incredibly hard for them by any means I have in my capabilities. So first, the weight of the objects. This will allow us to calculate the expected acceleration and compare it to the acceleration we actually detect. The first mass is 1.01 kilograms. The second mass is, let's just zero that. There we go. Second mass is, oh come on, stop turning off. The second mass is 1.108 kilograms. The third mass, I have to use the scales for because it's somewhat heavy, is, let's see, crap, gotta take it off. Oops. Right, here we go. That mass comes to, oh nice, 20 kilograms exactly. I swear that was a fluke. Alright. Third mass. This one's a bit heavier. In the position to pivot onto it. Third mass is, let's see, 21.4 kilograms. That will allow me to calculate our expected acceleration, which will be an important factor in validating the experiment. Right, now for the proofs, or things that will allow me to show I have eliminated variables and means I could have faked it. We have an analog clock, we have a digital clock. These will be hopefully visible and running through the entire time, which will show that I haven't mucked about with stop motion animating it or screwing about with the speed of it or anything like that. We then have a compass. This will show a constant magnetic field through the experiment. I have here an incredibly weak horseshoe magnet, to the extent that it can just about, yeah, pick up that, barely. It's enough to affect the compass. It also has no effect whatsoever on the rod, which is just swinging freely there. No movement there. And, well, can't expect to split a brick. They are just normal bricks I have split in half. In fact, they're on the same brick, so that's the same. But yeah, they have no effect. Well, it's a very weak thing, but yeah, move that away from the compass. Right, and I'll just prove that they do not have their own magnetic field. They are not electromagnets or anything of the sort. They will be freestanding on the rod. So yeah, all pointing north. Or what this compass thinks is north at the very least. Alright, I'll attempt to make all these visible from their stand up here, which is the closest I could get and still see the entire operation. Unfortunately, I can't film in landscape, which is what I would prefer, because my rudimentary stand there doesn't work. I don't have a dock for it. So I'm going to go and move the weights down to the far end for our control. I will move the bricks onto the system and let it stabilise. I want a time lapse for the next... Oh, what is the time? 8 o'clock. 3 hours. Next 3 hours I'll run time lapse of the system stabilising and finding its equilibrium position. And once that has occurred, I will move the two weights in without disturbing the system if entirely possible. I'll still have to wait for it to stabilise again. Once I move the weights into the system, I will then start the next time lapse of the entire thing rotating. If I can keep it going in the same time lapse, I will. Then after that, I will, after they hopefully have forced the system to rotate, and for the two bricks to contact the weights. Oh, I have a fresh from my garden, woodlouse. Once they've caused the system to rotate, I'll then remove the rocks, move them to the other side, and show it going in the opposite direction. So then I'll have a control, I'll have a movement in one direction, and movement in the other direction. That should show that there's no external forces in this system, which incidentally is tied directly onto the beam up there. So there's no risk of any motors or anything, and it's tied around there. So there should be nothing in the system that can cause any external forces whatsoever. Correct scientific practice is eliminating variables. And I hope with the equipment I have to hand, I would have eliminated them as much as possible. Right, so now I've got to put the weights on the system, move the rocks to the far end, and time-lapse the stabilisation. I will be doing that now. One last thing I forgot to mention is the feathers here, which are here to show that there's no prevailing breeze, or wind, or fan, or anything to push this thing round. It is entirely freestanding. As you can see, the slightest breeze, the feathers show it. Just replace them there. This is now freestanding, and I'm just about to set up the time lapse of it stabilising. Just going to remove everything. This is going downstairs. There we go. And this is not needed anymore. I have the two clocks, which are showing slightly out of time. 1 second. 8:01. There we go. And I have the compass, which I will attempt to make visible, showing that there is no magnetic field. Yeah, we're good. Alright, let's roll. Alright, this is one final video before I set up the control run. Be running from here. Looking down there, I have the two clocks, the compass, and nothing else. The start time is 8:08 plus however long it takes me to get the camera into position, and I think everything is good to go. Okay, so here we have it. The time is 12:55. We have the two masses in place. The mass system is at its equilibrium position, which is basically where the oscillations were centering about. I apologise for the foreshortened time lapse, but the phone was overheating, so I had to give it a bit of a rest. And so, based on that, where the equilibrium position from the videos was, is now the position it is at. These two are now attracting it away from the equilibrium position. I may move them around a bit more to give them a greater arc to act over. And I will find out what they have done in the morning. In the morning I should find both that and that resting firmly against the two rocks, because that will apply enough force to change the equilibrium position of this mass system to be further around the arc, because there's very little force in this system, as can be demonstrated from the fact that it took a little over, well, it started at 8 o'clock, so a little over 5 hours to stabilise is how little resistance there is in this system. I'm just going to move the rocks around a bit so that they act over a better arc, since it seems to be finding its own equilibrium position still a bit, and then we should be good to go. Right, so having reviewed last night's footage, it looks like when I put in the rocks, it still hadn't quite stabilised. Of course, the longer the time lapse, the faster the time lapse goes, and so it looks like there was a lot of movement that there wasn't. But I've got to make sure that the entire system is stable, and so I will be running it again. But today, this is going to be stabilising during the day. Since I've shown the stabilisation video, I'm not going to film it for the stabilisation stage, because, well, I want my phone for a start. But, yeah, it's just free swinging. It's nothing very special. The rocks are back down the end. You can just about see them down there. About there. And this is back free swinging and oscillating back into its neutral position. And this evening, I'll be doing that down there. Right, so let's switch out those lights. They point the light on. There we go, and we're done. I will be refilming tonight. Right, so here we have it. Despite the system not quite stabilising, as in the last time lapse, which I can only believe is due to the draft because I have left the cupboard, the thingy down there, open, I believe it is now at approximately the equilibrium position, which means if it comes to rest at any position other than a few degrees either way of this, I will have proven the attraction of masses. The expected result, based on the predictions made by Newton and Einstein, is that this will rotate around. It will move incredibly slowly because the forces are in the region of 1 × 10 to the minus 11. So very small amount of force, so 1 × 10 to the minus 11 newtons. So here we have it. Finally, Mark II of the experiment. After the first time the system was still rotating. This time I'm going to make sure that there are no drafts, because I think that's what's causing the kind of slightly weird oscillations. But they are oscillating about this approximate position. As they are oscillating about this position, that means this is the equilibrium position, point about which all the other forces are acting and knocking it backwards and forwards, which means if it comes to rest at any position other than this equilibrium position, I will have proven the attraction of gravity. It's still the same two rocks. The system has not changed in any way. So I've got the compass there pointing in the same direction, and the two clocks, and the mount. This will be the first one before I go away, which means I'll be able to finish off this experiment come Monday, I think. Yep. And at that point I will be reversing the direction and showing that it moves in the opposite direction after the system is restabilized. Okay, so let's see what answers I can get. Okay, so twice now I've run this, and both times it's come to rest at a position other than its equilibrium position, but both times I've had some inherent motion in the system. As you see in the time lapse, there was some slight swinging in the rod, although that's kind of a good thing because it's another proof is that this has come to rest at that position and is no longer swinging, which means that the force holding it there, in fact just off of it because it seems to be hanging in that general position, the force holding it there is greater than the forces that have been causing it to swing. But I still don't feel like this is conclusive, so I'm going to have to, I need the power cable unfortunately, but I will hopefully be able to pick this up again later on. But so far that's two tests, and both times they have come to rest at the position against the rock, even if there was still some motion in the system. So I hope to be able to get a situation where I manage to put it up perfectly, I don't have any motion in the system, although what's causing the motion I'm not entirely sure. Probably going to be down to drafts or something. But yeah, so look, we can hope to pick this up again. I'll try going in the other direction and hope it moves. So, an important time. We'll be turning the light on again. The wind has now died down. This has been up here, basically sitting just shy of the rock for the last couple of days or so. And I'm going to be placing the rock, the true attractors, approximately the same distance round that they were from the equilibrium position the other way, so that when it swings back to its equilibrium position, it will then be able to interact with the rocks and go back the other way. If it rests at that position, then I will have proven that the gravity is attracting and changing the equilibrium position of the oscillating rod. Unfortunately, I'm unable to measure the force of gravity because of my inconvenient camera position and the fact that I can't measure either speed or distance covered in order to get the values I need to apply the Suvat equations for a constant acceleration as an approximation of the acceleration of gravity based on the two masses, which is a bit of a pain. But we sent that off now, so that rock there will be going about here because the equilibrium position is through there. The other one will be going about up there somewhere, and hopefully we'll have as positive a result as I had going this way. And there we have it. Success. Gravity has been confirmed. We move from about 90 degrees around to this position and stabilized in this position. It's not oscillating, it's not swinging backwards and forwards. It stabilised and stayed there. So I find that pretty conclusive. It works in both directions. So I'm not sure what you're on about when you say gravity doesn't exist. It's a pretty simple experiment. Anyone can replicate. I just don't know why you haven't. Thank you.